Chapter 2, Water. So we went over the covalent bond and the hydrogen bonding in water, and we see that the hydrogen and oxygen they share their electrons unequally within the water molecule, and this is a polar covalent bond. And we also saw how we have sorry um, I'm sorry, let me come back. How we also saw how water is surrounded by four other water molecules, and each one develops a weak hydrogen bond between them. And so this hydrogen bond affects the properties of water, and as it supports life on Earth, water can be found as water vapor, as a liquid, or as ice, as a solid. It has many functions because of these properties of having hydrogen bonds. Water is an integral part of the body. About 40 to 60% of the body is made up of water. It transports. It has a lot of substances dissolved in it. Many of the solutes, like electrolytes, are dissolved in it. Blood has plasma, which is mainly 90% of plasma is made up of water, and you have other solids dissolved in it. It lubricates between body structures. We saw the serous membrane, how the parietal and the visceral membranes have a film of water in between, and that helps lubricate. Cushions, so for example, we have at every joint, you have bursa or tendons sheath, which is filled with, or the joints are filled with lubricating liquid, which is mainly water. And what unwanted substances like urine, it has mainly water, which are, and unwanted substances are dissolved in it, and which is easily eliminated. And the main properties of water which helps all these are cohesion, surface tension, and adhesion, and this is directly related to the hydrogen bonds. Uh, Cohesion is attraction between water molecules due to hydrogen bond. The best example of cohesion I can give you is how water is pulled by transpiration from the roots to the leaves, okay, against the gravity. And this is almost like pulling a chain from the roots up into the leaves. And on the surface of water, hydrogen bonds form almost like a film, and this help, I mean, they are so strong that they can actually um, withstand like heavy objects on them. And surface tension also pulls, like if there is a small space like which is microscopic and it's filled with water, it can draw closely with the help of cohesion and make the, for example, alveoli, it can cause it to collapse. And that's why we have a lipid molecule, almost like a detergent, called a surfactant, which is produced by the lungs cells, and that keeps the lungs opened up, the alveoli opened up. And then attraction between water molecules and substances other than water molecules, like your skin, right? So you have a film of water after you take a shower, and that is because of the skin and its attraction to water molecules. And these hydrogen bonds help in determining like some properties of water, like high specific heat and high heat of vaporization. What this means is that water can withstand changes in temperature much more than any other liquid. And it specific heat is defined as amount of energy required to increase temperature of 1 gram of a substance by 1 degree Celsius. And the water's value is extremely high. This has the highest specific heat because as the energy is taken to break the hydrogen bonds, they keep reforming because the molecules are constantly in motion. So it takes a lot for water molecules to break those bonds and escape as a gas. So this contributes to keeping the body temperature constant. And heat of vaporization, this is amount of heat required to release a molecule from a liquid state to gaseous state for that 1 gram. Again, it's really high due to hydrogen bonding. And that's why sweating cools the body, that particular feature. And water is a solvent of the body. I don't like to call it a universal solvent because lipids don't dissolve in it. So solutes are substances which can dissolve in water. If we have salt water, salt is a solute and water is the solvent. So it is pretty much inside the cell, outside the cell. So tissue fluids or blood, which is outside the cell. The main solvent in these cases are water, and there are many other solutes which are dissolved in it. And the substances which can dissolve are called as hydrophilic, and substances which do not dissolve are called as hydrophobic. So water can dissolve, some substances can dissolve but remain intact, for example, glucose. These are called as non-electrolytes. And then some substances can dissolve and dissociate, like sodium chloride, like any of these salts, right? And then acids and bases also can dissolve and break into ions. And these are called as electrolytes, which can conduct electricity. Substances which do not dissolve are called as hydrophobic. These are non-polar molecules, and we already saw that. And these are used for creating amphipathic molecules. And whenever you have non-polar substance in the blood, they have to be attached to a protein in order for it to move around in the blood. So what did you learn? So please draw the intermolecular bond that is significant in determining the properties of water, which is hydrogen bond. What property of water contributes to the need to produce surfactant and prevent collapse? That's surface tension. Which property contributes to body temperature regulation through sweating? That would be adhesion. Why is sweating less effective? That's heat of vaporization. Why is it less effective in cooling the body on a humid day? Because there's a lot of water content outside in the atmosphere as well. How does interaction of non-electrolyte and water differ from an interaction of an electrolyte and water? So you can talk about glucose and water, where glucose molecule really doesn't break down, it just dissolves in water. So when we talk about osmotic pressure, I will give an example of this, where a non-electrolyte like glucose contributes to like just one osmotic pressure. Whereas if you have an electrolyte, which may be much smaller than glucose, like sodium chloride, it dissociates into two parts, sodium and chloride. So the osmotic pressure for that is much higher than a non-electrolyte. So sodium chloride would be an electrolyte and glucose would be a non-electrolyte. And so you can draw how a phospholipid molecule interacts with water to form a membrane. Okay. And water is a neutral solvent. Oh yeah. So let's talk about acids and bases. So when water breaks down and to hydrogen ion and hydroxyl ions, it remains neutral because you have the same number of these two ions. If you add acid to that, then it produces hydrogen ions. Okay, it's a proton donor. Okay, and it increases the concentration of hydrogen ions. So if there is a particular acid which dissociates completely, right, it contributes to higher concentration of hydrogen ions, that is called as a strong acid, for example, hydrochloric acid. And if it does not dissociate or it contributes less amount of hydrogen ions, then it is called as a weak acid, like vinegar, right? You cannot expect to put your finger into hydrochloric acid and not be completely dissolved. But you can touch vinegar with your naked hands because it really doesn't dissolve or it doesn't dissociate that much of hydrogen ion concentrations. In the blood, we have an acid called as carbonic acid, which is H2CO3. I want you guys to remember this. This is carbonic acid, and it's a weak acid. Okay, so let me make it smaller. Oh well, I cannot. Okay. So anyway, okay, so H2CO3 or vinegar, those are all weak acids. So they produce hydrogen ions, and those are called as bases. And then you have, on the other spectrum, you have substances called as bases, which can accept hydrogen hydrogen ions because they dissociate to produce hydroxyl ions. So if they absorb more hydrogen ions, those are stronger bases like ammonia or bleach. If they less absorb, then those are called as weak bases. For example, we have dish detergent, right? So those are all weaker bases. In the blood, bicarbonate is a weaker base. So we have carbonic acid, which is a weak acid, and we have bicarbonate, which is a weak base. Okay, sodium bicarbonate is what we have in our bodies. All right, so those are the two. So why do we need weak acids and weak bases in our blood? That is mainly to neutralize the acids and bases. So before we do that, let's talk a little bit about pH. pH is a scale which mainly is used to measure hydrogen ion concentration, and it ranges from 0 to 14. So I like to call it 1 to 14. So strong acids are 1, and strong base is 14. And in the middle, we have 7, which is neutral. So at 7, water dissociates to produce 1 divided by 7 zeros of hydrogen ion and OH ions. And this is called as a log value. Okay, so inverse of a log for given hydrogen ion concentration. So when we talk about hydrogen ion, if the hydrogen ion concentration increases, the pH decreases. If the hydrogen ion concentration decreases, then the pH increases. Right. So when we interpret the pH scale, let me go into the scale right here. So we have 1 to 14. So from 7, if we go this way, that is increasing acidity. So as the pH decreases, the acidity increases. As the pH increases, the basic or the base increases. So this is neutral. So here you can see that as it becomes acidic, the hydrogen ion number of hydrogen ions increase. And as the basic increases from 7 to 14, you can see OH ions are increasing. So here are some of the examples, like 1 is hydrochloric acid, 2 is lemon juice or stomach acid, and so on and so forth. Urine is about 6, depends on what kind of food you have. Vegetarian food is more alkaline, it's about 8. With meat produces urine, which is more at 6. Milk and saliva is 6.3, 6.6. Pure water is 7. Blood, however, is going to be 7.4. Okay, so this is something that you have to remember. And then you can see that most of the household cleaners are all basic. A strong base is sodium hydroxide. Strong acid is hydrochloric acid. Strong base is sodium hydroxide. And each of these numbers, they differ by 10 times, right? So they're 10 times stronger. So suppose I take pH 5 and pH 3. pH 3 is a stronger acid as compared to pH 5, and this is 100 times stronger than 5. Not 2 times, not 20 times, 100 times. So that is 3 to 4 is 10, 4 to 5 is 10, 10 times 10 is 100. Okay, so please do remember that. So how we use this in our system is, so whenever you have an acid or a base solution, and acids can be neutralized by base. So these are called as buffers. So suppose you have a strong acid like hydrochloric acid, a weak base is added to that, okay, and that converts to a weak acid and water. So bases are neutralized by adding acid, acids are neutralized by adding base. So these are called as buffers, and they help in preventing the pH changes, okay, in the blood. Blood has to be between 7.35 and 7.45. So the buffers that are used is carbonic acid, which is a weak acid, and bicarbonate, which is a weak base. So these are added to convert them. So that is why buffers are really important, because if the pH falls below 7.35, at 7, a person is dead. Okay, and similarly, if it is more than 7.45, at about 7.6, a person stops, the functions stop, so stops breathing basically. So it's very crucial that the blood pH needs to remain between 7.35 and 7.45. Smallest things like vomiting can change your pH, diarrhea can change your pH, alcoholism can change your pH. Some diseases like cystic fibrosis or any respiratory illness or kidney failure can change the pH, and even the way we breathe, right? If we hold our breath or we hyperventilate, the pH changes. So constantly, these buffers are working to bring the blood pH back to normal. So you can answer those questions.